There are four primary supervised fine-tuning methods: instructions, task-specific, domain adaptation, and hyperparameter tuning. Instruction fine-tuning typically involves training an LLM using prompts or instructions provided alongside the input data. In this BERT example, two input statements are shown. And these input statements are suitable for tasks such as generating clinical documentation or summarizing medical records for a special patient, which are common in medical applications. In this code snippet, trained text contains the two instruction prompts. Tokenizer tokenizes the prompts using the tokenizer and pads and/or truncates them to ensure uniform length, preparing the input data for further processing or model training. In the line, train encodings equal tokenizer, the tokenizer object is being used to process the list of text inputs, train_text. The tokenizer function processes the train_text list according to the specified truncation and padding settings, returning a dictionary of tokenized inputs called train_codings. Each key in the dictionary corresponds to a different attribute of the tokenized inputs, for example, input IDs or attention masks, and the values are lists containing the corresponding tokenized representations for each input in train_text. These tokenized representations are numerical and can be directly fed into a machine learning model for training or inference. Let's take this opportunity to dive a bit deeper. When the input text is tokenized, it is broken down into individual tokens, where each token corresponds to a word or subword in the text. The tokenizer then assigns a numerical token ID to each token. For example, the summarized token ID here is 5060. Attention masks allow us to send a batch of tokens into the transformer even when the examples in the batch have different lengths. In BERT, we do this by padding all sequence to the same length, then using the attention mask tensor to indicate which tokens in each sequence are actual input tokens and which are padding tokens. This allows the model to ignore the padding tokens during processing by assigning them a value of 0 in the attention mechanism, ensuring that only the relevant input tokens receive attention. This code snippet iterates over each input text's attention mask and prints it. Wherever the attention mask has a value of 1, it indicates that the corresponding token in the input sequence is an actual input token. A value of 0 indicates that the corresponding token is a padding token. Recall that pre-trained LLMs are trained on a large corpus of text data. This pre-trained model has learned general language patterns and semantic representation from this data. If you have a use case or domain use case, you need to customize the model using task-specific fine-tuning. This fine-tuning involves taking the pre-trained LLMs and further training it on a smaller dataset that is targeted to the task at hand. For example, sentiment analysis, text classification, or question answering. This code defines a task-targeted dataset for sentiment analysis. Text is a variable that stores a list of text samples or examples for sentiment analysis. Labels is a variable that stores a list of sentiment labels. In this example, sentiment labels are encoded with integers, 0 for negative sentiment, 1 for neutral sentiment, and 2 for positive sentiment. During fine-tuning, the pre-trained model learns to predict the sentiment labels based on the input text samples. Domain fine-tuning involves fine-tuning a pre-trained model on a domain-targeted dataset to adapt it to the characteristics of that domain. This process typically involves providing labeled examples from the targeted domain to the model during fine-tuning. In this example, the variable medical_text contains concrete medical examples such as patient symptoms, diagnostic results, and medical conditions. When fine-tuning a model on this dataset, the model will learn to generate text that is consistent with the medical domain based on the provided examples. Let's use this opportunity to compare the difference between how BERT and GPT handle attention masks during our domain example. As we saw earlier in the video, BERT requires explicit padding to ensure that all input sequences within a batch have the same length. GPT does not require explicit padding because all tokens are considered as input tokens, and there are no padding tokens. Basic hyperparameter tuning in an LLM involves optimizing the hyperparameters that control the training process of the model. There are many hyperparameter techniques, and in this example, batch size, learning rate, and the number of epochs is shown. Hyperparameters related to the architecture of the model, such as the number of layers, hidden units, attention heads, etc., can significantly affect the model's capacity and performance.